This video covers chapter 4 of the Higher Collins book, and this chapter is basically about sequences and their rules. And there are two types of sequences we're going to be focusing on, and they are linear sequences and quadratic sequences. So let's just run through the main differences. So a linear sequence, we have something that we call a constant difference. So in other words, to get to the next number, you add or you subtract a value. So you add or subtract to get the next term. Okay, and we'll look at how we find the rule for a linear sequence in a moment. In a quadratic sequence, we have a constant second difference. So not the difference between each number. We have a constant second difference for a quadratic sequence. A linear sequence always looks like this: a n plus b. So n is a number we're going to find, sorry, a is a number we're going to find. So we need to work out what a is. And b is a number we need to find. Now b could be positive or negative. So let me just put here plus minus. So it could be plus or minus b. And we need to find both these values. So a and b are just basically numbers. Normally whole numbers, but not always. And we'll need to work out what those numbers are, and I'll show you how to do it in a moment. A quadratic sequence has this sort of pattern: something an squared plus bn plus c, and on this we need to work out what a is, what b is, and what c is. Now again, actually just circle the letters. Again, these bits here could be positive or negative. Here we need to work out what numbers go here. Yeah, and they're going to be numbers just like in a linear sequence, and I'm going to show you how to work out those numbers. And in both of them you see the letter n. N basically stands for the position. Yeah, so if I want to find the first number, I'll make n equal to 1. If I want to find the second number, I'll make n equal to 2, and so on. And these positions, the proper name for them is term. So we might want to find the first term, the second term, the third term. Okay, and what we need to be able to do is to substitute into the rule for a linear or quadratic sequence and actually work out what these rules are. Okay, so let's start by the rule for a linear sequence. So that's going to be actually this bit here where we said we can substitute into the nth term for a linear sequence. Okay, so let's see what that looks like. So let's say I had the rule for a sequence was 3n minus 7, and let's say that's our rule, and I want to find the first term in that sequence. So what I do, I make n equal to 1, so n equals 1. So what I'll have is 3 times 1 minus 7, which is 3 minus 7. So the first term in the sequence is going to be negative 4. So I want to find the second term in that sequence. So now I make n equal to 2. So that would be 3 times 2, which is 6. 6 minus 7, negative 1. If I want to find the third term in the sequence, I'll make n equal to 3. So then I'll do 3 times 3 minus 7, which is 9 minus 7, which is 2. And let's go all the way to the 50th term in the sequence. So to find the 50th term, I'll just make n equal to 50. So I will do 3 times 50 minus 7, which is 150 minus 7. That gives me 143. So I'm just going to underline where I've substituted n for the position that I want. Yeah, first we make n equal to 1, second n equal to 2, third n equal to 3, 50th or any one n equal to 50. So that is substituting into a linear sequence. Okay, let's have a look at the next thing below it, which is substituting into, now it's actually down here, generate terms of a quadratic sequence. So we're sort of jumping a bit. Generate terms in a quadratic sequence given the nth term. So let's have a look at this one, jumping around a bit. Let's say I had 2n squared minus 5n plus 4, and let's say that's my nth term rule for quadratic sequence. First term, just like we do with a linear sequence, I make n equal to 1. Now that would be, it's a little bit more complicated to substitute, but still the same thing. 2 times 1 squared minus 5 times 1 plus 4. Okay, so that's 2 minus 5, which is negative 3, plus 4, which is 1. So the first term is 1. Second term. So n is 2. So I have 2 times 2 squared minus 5 times 2 plus 4. We can work out what that is. So I'm just going to underline here what I've substituted. First term, 1 goes there, 1 goes there. Second term, 2 goes here, 2 goes here. Now, to work this out, we need the rules of BODMAS. So we need to work out what 2 squared is first here. 2 squared is 4, so you do 2 times 4, which is 8. Then you're going to have, this is 10, so 8 minus 10 is negative 2. Then negative 2 plus 4 gives me 2. Okay, let's do the third term. So n is 3, so 2 times 3 squared minus 5 times 3 plus 4. So again, let's underline third term, 3 there, 3 here. So that's going to be 3 squared is 9, 2 times 9 is 18. 18 minus 15 is 3. 3 plus 4 is 7. And so on. Okay, so that's how we substitute into a quadratic sequence. Same type of thing as we do with a linear sequence. Let's jump back to the list we were looking at, and let's go back here. Understand how prime, odd and even numbers interact with addition, subtraction and multiplication. Okay, there's not really a lot to say about this. It's basically what happens when you do odd plus odd and even times even. So I'm going to use the letter O for odd. I'm going to use the letter E for even. And let's just go through what happens when we do different calculations. So if I do an odd number plus an odd number, I always get an even. Let's think of an example, 7 plus 5, both odd, I get an even. If I do an odd plus an even, or an even plus an odd, I'm always going to get an odd answer. Again, just think of an example of an odd number and an even number. And if I do an even plus an even, I always get an even answer. Okay, so that's what happens when we add and subtract, or sorry, when we add. For subtracting, the rules are also the same. So I'm going to add a minus sign as well here. When you subtract, the same rules apply. Let's look at multiplying and dividing. If I do odd times odd, so let's think of two odd numbers multiplied together. 3 times 5 is 15, that's odd. Let's think of two different ones. 5 times 7 is 35, that's odd. So odd times odd is odd. Odd times even, or even times odd, that's always going to be even. You can think of some examples of that. And even times by even is always going to be even. So that's this bit here about how odd and even numbers interact in these types of problems, and probably also with prime numbers as well. Now, apart from 2, all the prime numbers are odd. Let's write that down. Apart from 2, all primes are odd, aren't they? So that means we can sort of use the rules we've got here for these odd and even numbers for primes apart from 2 really, and we could say, right, okay, you know, sometimes if you add primes together they're even, sometimes they're odd. It all depends on which primes. Yeah, but if we remember that 2 is the only even prime number, then when we look at these rules, and maybe we might want to write some rules about what happens when we multiply, add or subtract odd and even numbers, we can say something about primes as well. 2 will be the exception, but every other prime number is odd, so we're going to be looking at these rules where you've just got odd numbers. So 2 will maybe help us find an exception to the rule. Right, finding the nth term of a linear sequence. So this is this bit here. Nth term of a linear sequence. Right, very easy. Right, the nth term for a linear sequence, as I said, always follows this pattern, a n plus b, where n is the position number. A is the jump between each number in the sequence. Now that might be a jump that goes up or a jump that goes down. And b, this number here, could be positive or negative. It's the number before the first number in the sequence. So the number before, or the term before the first term or number in the sequence, and I'm going to call it the nth term. So like you've got the first term, the second term, let's call it the nth term. If we can find those two things, then we've got the nth term rule. So here's a sequence, 7, 12, 17, 22, 27, and so on. This one goes on forever. Right, so the first thing we need to do is to find the jump. What's the jump between each number? Well, this goes up by 5. So if we start to write the nth term rule, we write 5n, the jump in front of n. That's a. A is like the jump, it's 5. Okay, since it goes up in 5s, what number came before the first number? Well, that number, the nth term, must be 2. So we'll put a 2 there. So the nth term rule for this sequence is 5n plus 2, because the number before the first number was a plus 2, not a minus 2. Okay, here's a different sequence. Let's work this out. So let's have negative 8, negative 12, negative 16, negative 20, and so on. So what's the jump this time? Well, can you see this one's going down by 4? Negative 4, negative 4, negative 4. So we start by writing negative 4n, because the jump is going down. Then we want the number before the first one. Now we need to be careful. Have a look at the pattern. If this is going down by 4, the number before the first one was negative 4. So we have negative 4n minus 4. Let's try one more. So let's have negative 1, 6, 13, 20, and so on. Right, so let's look at the jump. This is going up by 7. So we start by writing 7n. Then we want to find a number before the first one, so we need to be careful. If it's going up by 7, the number before the first one isn't 8. It's actually negative 8. Negative 8 plus 7 is going to be negative 1, so negative 8. So the nth term rule is 7n minus 8. So that's how we find the nth term rule for a linear sequence. Let's jump now to a quadratic sequence. So we're now going to be looking at this bit here. This is probably the hardest bit, and then we'll jump to the other special sequences in a moment. So we've got some sort of quadratic sequence and we want to find the nth term rule. So this one goes, it's going to start with 9, then 20, then 33, then 48, and then 65. Okay, now with any type of sequence we always start by working out what this difference is. Now with a linear sequence this difference is the same, so this goes up by 11, then 13, then 15, then 17. Now because it keeps changing, this is not a linear sequence, but if we look at the difference of the differences, what we call the second difference here, can you see that the differences always go up by 2? This tells us it's a quadratic sequence. I'll just put a little note here. So if the second difference is constant, that means it doesn't change. Okay, the sequence is quadratic. Okay, so this tells us it's a quadratic sequence. Now the rule for a quadratic sequence is an squared plus bn or minus bn plus or minus c, and we need to work out these values of a, b and c. Right, okay, a is very easy to work out. A, this number that goes here, okay, it's half of the second difference. Whatever the second difference is, it's half of that. Now I can see the second difference is 2. Yeah, let's just highlight it. There's the second difference. Now half of 2 is 1. So the number that goes where a is 1. So I'm going to start to write my answer down here. So I'll start by writing 1n squared. So that 1 came from half of that number, half of the second difference. If that second difference was 4, then half of 4 would be 2. It'd be 2n squared. So whatever that second difference is, you halve the number, you get the value in front of n squared. In this case, it's 1. Step number 2. Step number 2, we're now going to write out the sequence again. So 9, this is the original sequence, 9, 20, 33, 48, 65. And what I'm going to do, I'm going to subtract the sequence that 1n squared gives me. So this is the first part of the rule, and I'm going to use this rule to generate a sequence down here, which I'm going to subtract from the original sequence because I've already got this bit. Let's take it away and see what's left. Now what this means is 1 times n squared, which means 1 times square numbers. So this 1n squared, which we're going to write down a sequence of, this means 1 times square numbers. Now the square numbers, I'll write them at the top here, are 1, 4, 9, 16, 25, 36 and so on. Okay, these are our square numbers. And 1n squared says, so they're square numbers, they're n squared. What this rule is telling me here is to take the square numbers and multiply them by 1. Now, if this second difference was 4, then half of that would be 2. I would have 2n squared. What would I do? I would do 2 times the square numbers. So I'll take my square numbers here and double them. But it doesn't say 2n squared because that doesn't say 4. So 1 times the square numbers, that's basically the square numbers. So that's going to be 1, 4, 9, 16, and 1, 4, 9, 16 and 25. So I'm going to take these numbers away from the original sequence. So this line of working here is 1n squared. Right, and this line of working here, this is the original sequence. This is basically the question. And we always do that. The question numbers take away 1n squared or 2n squared. It might even be half n squared. It all depends on that second difference. Right, let's work these out. So 9 minus 1 is 8. 24 minus 4 is 16. 33 minus 9 is 24. 48 minus 16 is 32. And 65 minus 25 is 40. Now we're almost finished. We look at what we've now got. So I did the original sequence minus 1 times square numbers, and I'm left with this. Now all we do is find the nth term rule of that sequence. So we take these numbers that we've just worked out, and what we're going to do is find the nth term rule of that sequence using exactly the same method that we used for a linear sequence. Now this sequence goes up in 8s, so I write 8n. You can see that the jump between each number goes up by 8, like that. And the nth term, the number before the first one, would be 0. 8n plus 0. Now this completes my answer. This is this part here. And all I do is put together the part that I got from before, 1n squared, and then I put this on the end. So this 1n squared, a is 1, b happens to be the number 8 plus 8, and c is 0. So final answer, 1n squared plus 8n plus 8, or plus 0. Now we don't need the 1, so we can just write n squared. We don't need a 0, we can just write 8n, and that will be my final answer. We'll do one more in a moment, and we'll find the nth term rule, and then we'll look at some of these power sequences. So one more example of this, finding the nth term rule for a quadratic sequence. Right, this time the sequence is 2, no, not 2, we'll start with 5, 18, 35, 56, 81, and we'll stop there, and it carries on like that. Step number 1, look at the difference. So I can see that I add 13, then 17, then 21, then 25. Okay, it's not linear because that first difference is changing, so we look at the second difference, and every time the differences go up by 4. Step number 1. Right, half of 4 is 2, so straight away I can write down 2n squared. That's half the second difference. Right, next step, write down the original sequence, 5, 18, 35, 56, 81. We're going to subtract the sequence 2n squared. That's what we just got from the first part. That is the square numbers 1, 4, 9, 16, 25, 36. It's those square numbers doubled. So it's 2, double 1, double 4, 8, double 9, 18, double 16, 32, double 25, 50. Yeah, 2n squared are square numbers doubled. Right, let's subtract. 5 minus 2 is 3. 18 minus 8 is 10. 35 minus 18 is 17. 56 minus 32 is 24. And 81 minus 50 is going to be 31. Right, almost done. We now find the nth term rule of this. Now what does this do? This goes up in 7s, so it's 7n. If it goes up in 7s, like this, plus 7, plus 7, plus 7, plus 7, what number came before the first one? Well, that would be the number -4 if it goes up in 7. So the sequence term, or the rule, is 7n minus 4. That we stick on the end of this to get the final answer, which would be 2n squared plus 7n minus 4. So that completes our nth term rule. The last thing we need to look at are geometric sequences and some special geometric sequences. So geometric sequence, which you'll find here, that's very easy. These are sequences where you multiply to find the next number. So times to find the next number in the sequence or the next term. Here's an example of a geometric sequence: 2, 6, 18, 54, and so on. Now if I have a look, I'm timesing by 3 to get the next number in the sequence. So this is what we call a geometric sequence, one where you times to get the next number in a sequence. You do need to know how to write the nth term rule for a couple of geometric sequences. The most important ones are powers of 2 and powers of 10. Okay, so powers of 2 would be a sequence that goes 2, 4, 8, 16, where you double each time, 32. Okay, the nth term rule for this is 2 to the power n. And powers of 10, well, that's 10, 100, 1000, and so on. The rule for this would be 10 to the power of n. And lastly, the last thing to finish off with is Fibonacci sequence. So I'll just highlight that. So that is this bit here. Recognize special patterns such as Fibonacci sequence. Right, so Fibonacci, Italian mathematician, and he sort of found all sorts of patterns in numbers. And a Fibonacci sequence is basically where you add the last two numbers to get the next one. Now we often start a Fibonacci with the numbers 1 and 1. So you start with a 1 and a 1, add those together, you get 2. Add the last 2, you get 3. Add the last 2, you get 5. Add the last 2, you get 8, 13, and so on. You add the last two numbers. Now you don't have to start with 1 and 1. You can start with any numbers. What if I had a Fibonacci sequence where I started with 5 and let's go a bit crazy, -2. Now if I add those together, I get 3. If I add those together, -2 plus 3, I get 1. If I add those together, I get 4. If I add those together, you get 5, and then 9, and then 14. Yeah, so you can start with any two numbers, but generally we start with the numbers 1 and 1. So that now covers all the work in chapter 4 of the textbook, which covers sequences.